Hey guys, welcome back. So in the last video we talked about the loss or cost function. That was the MSE or mean squared error, and we also learned about the general hypothesis function. That was the result of passing our training data to a learning algorithm. In this case that was a simple linear regression model. As you can see here, that our function f of x is equal to wx plus b. So f is a function of x in respect to the value of w and b. And we also looked at our cost function. That was a j, also a function of w and b, and that was 1 by 2m of the sigma of fwb of xi minus yi and whole square, and we had to sum them all up because we are going to calculate the total cost for every data points I that I have. This m is actually the number of data points that we have in our data set. So today let's just look at more specific cases where in our model the value of b is equal to 0, and then you will see how our model is behaving if it's only the function of x but with respect to the value of w. So let's say we write our general model as f of wb is equal to wx plus b, and we assume that b in this case is equal to 0. So in that case our model would be f of wx is equal to wx. So in this case our model is now a function of x with respect to only w or weight or parameter. And if we take a look a deeper look at our model, we find out that our model is now is only the function of x. So whatever value x is taking is just multiplied by w. So in that case we will also have a different cost or loss function. So let's say if a model is f of wx is equal to wx, how our cost function would look like. So cost function j would be only a function of w, 1 by 2m sigma I is equal to 1 up to m, and then here our predicted value, that is the f of wb, will only be f of w because the term b is equal to 0. It does not have any effect in the overall equation. So we will say f of w xi minus yi squared. And this is how our cost function would look like if in our model the term b is equal to 0. So let me just plot some values of w on the graph, on the Cartesian graph, and then we will take a look at the cost function as well. All right, so we have our hypothesis function f of x, which is a function of x with respect to w is equal to wx, while b is equal to 0, and our cost function j, w is equal to w, which is a function of w. So we have some training data, or the value for x in this case, which are 1, 2, 3. We have the respective value of y, which are 1, 2, 3 as well. So what we're going to do is we are going to give the values of x to our hypothesis function, and then we are trying to find the y hat of I for the different value of 1, 2, 3 in respect to the value of w, which we start with some random values of 1 and then 0 0.5 and then 0 n minus 0 0.5. So let me just draw the actual values of x and y on the Cartesian plan. So we have x, so this is how it is. So we have 1 1 and then so this is our training data. So that's exactly the line, but since I'm just drawing with the pencil, it's not really easy to fit the line exactly to the point, but that's just sort of give you a general idea of how our actual line of y is passing through the data. So what we do now, we're going to calculate the different values of y hat of I for the different value of x, which are 1 2 3. So if x is equal to 1 and w is equal to 1, so our y hat would be exactly the same point. Let me just change the color. So it'll be exactly the same point that you see here. Then if we feed a line to that, that is actually the line that's passing through the exact points of y, I, and therefore the cost for w1 for the value of w when it is 1, then j of w is equal to 0, because remember the cost is nothing but the y hat of y minus yi, which in this case y and y hats are exactly the same point, so the cost is equal to 0. Then if we have the value of w is equal to 0 0.5, then I've calculated the value of j of w, which is 0 0.58. So let me just plot that on our hypothesis function first. So if our w is equal to 0 0.5, then if we plug that value into our hypothesis function, f of x in respect to w, which is wx, then it's going to make the value of f of x half of the value that we have. So it's going to be this line. So if you find the cost is nothing but the difference between the yi, which is this point, and y hat of y, which is this point. So the cost would be y hat of y minus yi, which in this case is not equal to 0. And I've just calculated that the value for j of w is equal to 0 0.58. And then for a different value of w, which is equal to 0, if we just plug the value into our hypothesis function, then all the value of f of x in respect to w will be 0. So this is actually the point that we have. In that case, our cost function, which is nothing but the difference between the yi and y hat of I, which is this distance, would be, so j of w in this case would be 2.3. I've just calculated that using the cost function, the same function that I mentioned, and that is, so it's a little bit time consuming to calculate every point using the same cost function that I mentioned earlier, but you could just do that. I've just calculated that just a while ago. I'm just going to give the value and then give you the respective output, and then we're going to plot the cost function, and then we'll see how the cost function would look like. So I also give the value of w as minus 0.5, and then we calculated the f of x, which is the function of x with respect to w, which is wx. Then the line would be somewhere here, so and the cost will be yi minus yi hat, and when I just calculated, the J of W was 5.25. So let me just plot the J of W here. So if W was equal to 1, then J of W was equal to 0. So if W was equal to 0, then the 0.5, in this case here, the J of W was somewhere here, and if W was equal to 0, the JW was somewhere here, 2.3, and if the W was minus 0.5 here, then the the J of W was 5.2 somewhere here. And I noticed that when I give the W bigger and bigger value, for example, if W was equal to 2, the respective JW was somewhere here. So I found a number of values here with the different values of W. Then when I plotted the graph of JW, notice that this is JW, this is W. So this is the value of JW on the y-axis. I noticed that the graph of GW, which is the cost function of our linear regression model, in this case our hypothesis function, is a soup bowl shape function, which has a minimum point here, and that minimum point is exactly the cost that we are looking for. So looking at this example, you saw that when the value of W was equal to 1, in case that B was equal to 0, our model, the line of f of x in respect to W, which is EWX, was fitting our data perfectly. And that was the line that I just showed you here. So remember that in linear regression, what we are going to do, we are going to look for the line that is passing through our data perfectly, and that's fitting all the data points along. So one thing that I have to mention here is that if our data points is small, so we just calculated the value of W, we just sort of did a trial and error so that we find the best value of W that could fit a line to our data. But if the value or if our data points are increasing to, let's say, hundreds and thousands of samples, that's really hard for us to calculate and find the best value of W for our model. So that's when a very handy algorithms come in, which is called the GD, in short, the gradient descent algorithms, which allows us to find the best value of W for a model. That will be the topic for the next video, and I'm looking forward to see you in the next video, which I'm explaining the gradient descent algorithm. Thanks for watching.